You know how sometimes you look at the ground, just the dirt under your feet, and it seems, well, kind of boring, just sitting there? Well, get ready, because what if I told you it's actually this incredibly busy place full of amazing stories about how our world works? Today on the deep dive, we're digging in literally. We're exploring something called superficial deposits. Sounds fancy, I know.
Yeah.
But really, it just means all that stuff, sand, soil, gravel, rocks that covers the hard bedrock way down below, like a big, messy blanket on the earth.
Exactly. And our mission today is to unpack how this stuff gets made, how it moves around, and how it shapes, well, everything you see.
And we want to make it super clear, really straightforward, almost like we're explaining it to someone seeing the world for the very first time, full of curiosity.
Making the complex simple, that's the goal.
So why should you care? Because understanding this is like getting a shortcut to figuring out the ground you walk on, the soil where food grows, even where we build our houses and roads. It's fundamental stuff.
It really is. We walk on it every day. But there's so much going on.
Yeah.
These superficial deposits, this mantle of surface material,
Yeah.
it's not just static dirt, it's dynamic.
It's the stuff on top, right?
That's a good way to put it. The stuff you can dig into easily.
Okay, so here's something I find fascinating. The word soil. A geologist, a rock expert thinks of soil completely differently than an engineer who builds things.
Oh, absolutely. That's a classic point of confusion, but it's crucial.
How so?
Well, for a geologist, soil is really specific.
Yeah.
It means rock that crumbled down right there in its original spot. Didn't move.
Like crumbs left right where the cookie broke.
Exactly like that. We call them residual deposits. They've resided there.
Mm.
Or sedentary sitting still.
Okay, residual. Got it. But the engineer.
The engineer has a much broader view. To them, pretty much any loose stuff on the surface they can dig without explosives is soil.
So that includes the residual stuff and anything else that got moved.
Precisely. Wind-blown sand, river mud, glacial till. If you can dig it, it's often just called soil in engineering terms.
Wow. Why does that difference matter so much?
Think about building, say, a bridge or a house. The engineer needs to know what that ground is like. Is it strong? Will it shift? Knowing if it formed right there or traveled tells them loads about its properties, how stable it is, how water flows through it. It's fundamental for safety and design.
Yeah.
You wouldn't build a sandcastle on mushy mud right now. Same principle, just bigger stakes.
Makes sense. So, okay, back to basics. How does solid rock turn into this loose stuff in the first place?
Right, that's the starting point. It's a process called weathering. Basically, nature's way of breaking down hard rocks into smaller bits. It's how you get the ingredients for soil.
Nature's rock crusher.
Kind of, yeah. And it happens in three main ways, often working together.
Okay, what's the first one?
Mechanical weathering, sometimes called physical weathering. This is just breaking the rock into smaller pieces without changing its chemical makeup.
Like smashing a rock with a hammer. The pieces are still the same type of rock, just smaller.
Exactly. And nature has its own hammers. One big one is frost wedging. Water seeps into cracks, freezes overnight.
And water expands when it freezes.
Right. That expansion acts like a wedge, pushing the rock apart. Super powerful in cold places.
Cool. What else?
There's salt crystallization, where salt dissolved in water gets into pores, the water evaporates, and the salt crystals grow, pushing things apart. Similar idea.
Huh. Little crystals doing that.
Yep. And hydration, some minerals absorb water and swell up, causing stress. And then abrasion, which is just rocks bumping and grinding against each other. Think rivers, tumbling rocks, or wind blasting sand against a cliff face, like natural sandpaper.
Okay, so that's physical breakup. What's next?
Chemical weathering. This is different because the rock minerals actually change. They react chemically and turn into new substances.
So it's not just smaller bits, it's different stuff.
Exactly. Think of hydration again, but chemically water, combining with minerals to form totally new, often weaker minerals, like feldspar turning into clay.
Okay.
Then there's carbonation. Rainwater picks up CO2 from the air, making a weak acid, carbonic acid, like fizzy water, basically.
And that dissolves rock.
It's particularly good at dissolving limestone. Caves are often formed this way. Then there's oxidation, think rusting. Oxygen reacts with iron in minerals.
Like on an old car.
Same idea. Forms iron oxides, like hematite, which often gives soils that reddish color. And sometimes minerals just dissolve in water. That's solution.
Wow. Okay. So physical breaking, chemical changing. What's the third one?
Biological weathering. This is where life gets involved, living things.
Like plants and animals.
Yep. The most obvious is root action. Plant roots grow into cracks.
And force them wider. I've seen that on sidewalks.
Exactly. Nature's little crowbars. Also, decaying plants release organic acids, which can chemically dissolve minerals. And even tiny microorganisms like bacteria or lichens clinging to a rock face can slowly extract nutrients and weaken the rock surface.
It all works together, huh?
Absolutely. And climate plays a huge role. Cold, wet places, lots of frost wedging; hot, humid places, chemical weathering goes into overdrive.
Right. So rocks break down. Now, you mentioned some of this stuff stays put, the residual soil.
That's right. Sometimes the weathered material just sits there, right on top of the parent rock it came from. And it develops layers, like a cake. We call these layers soil horizons.
Layers, like stripes in the dirt.
Kind of, if you dug a pit, you'd see them. Right at the top, maybe some leaves and twigs. That's the O horizon, for organic.
Okay, the surface litter.
Below that is the A horizon, or topsoil. Darker usually, lots of biological activity. Minerals often get dissolved here and washed downwards.
It's like water draining through coffee grounds.
Good analogy. Those dissolved minerals can then accumulate in the layer below, the B horizon or subsoil. Often denser, maybe more clayey or reddish from those iron oxides.
Oh, okay. OAB.
Then you get to the C horizon. This is partly weathered bedrock. You can still see bits of the original rock structure, but it's starting to crumble. It's the transition zone.
Getting closer to the source rock.
Exactly. And finally, the R horizon, Arbor rock. That's the solid, unweathered bedrock underneath it all.
The base layer. OABCR.
Got it. And engineers have their own system, too.
They do. They grade the rock based on how weathered it is, which is super important for knowing its strength. It goes from grade 1 to grade 6.
Okay, quick rundown.
Sure. Grade 1 is fresh rock, looks perfect. Grade 2, slightly weathered, just some surface staining maybe, still really strong.
Easy enough.
Grade 3, moderately weathered. Less than half the rock material has turned into soil. Grade 4, highly weathered, now more than half is soil. Getting much weaker.
Grade 5 is completely weathered. It's all soil now, technically, but you can often still see the original textures or structures of the rock it came from, like a ghost image.
Whoa.
And grade 6 is residual soil. All original rock fabric is gone. It's just soil formed in place.
That's a really useful scale for building things, I bet.
Definitely. Tells you a lot about how it will behave.
Okay, so that covers the stuff that stays put. But you said most superficial deposits have actually moved the travelers.
That's right. Most of the stuff on top has been transported by wind, water, ice, or even gravity. These are transported deposits. And knowing the transport mechanism tells you a lot about the deposit.
Like how it got there explains what it's like.
Exactly. Let's start with wind. We call these aeolian deposits. Wind is great at sorting. It picks up the fine stuff and leaves coarse stuff behind.
Where do you find these? Deserts?
Deserts, yes, but also areas that used to be near glaciers or sandy coastlines. Think of low as thick blankets of windblown silt. Very fine stuff. Can form steep cliffs, but it's easily eroded.
Like dust blown over huge areas.
Yep. And of course, sand dunes. Hills of sand constantly shifting unless vegetation anchors them down.
Got it. Wind. What's next?
Rivers. We call river deposits alluvial deposits, or alluvium. Rivers are constantly eroding, transporting, and depositing sediment.
Makes sense. Rivers carry mud.
Lots of it. They create things like alluvial fans, fan-shaped piles of sediment dropped, where a fast mountain stream hits a flat valley and slows down, spreading out its load.
Like dumping a bucket of sandy water on the floor.
Sort of, yeah.
Yeah.
And deltas, where a river meets a lake or the ocean and drops everything it's carrying because the flow stops, often triangular, hence the name.
Right, like the Nile Delta.
Exactly. Also, floodplain deposits layers of silt and clay left behind when a river floods its banks. Makes for very fertile farmland. And river terraces, which are like steps on the valley sides, old floodplains left high and dry as the river cut down deeper over time.
Okay, wind, water. What about ice?
Glacial deposits. Glaciers are incredibly powerful movers. They scrape and pluck rock and carry everything from huge boulders down to fine clay, all mixed together.
Like giant, slow bulldozers made of ice.
Pretty much.
Yeah.
When the ice melts, it dumps this material. The most common stuff is called till, or sometimes boulder clay. It's just a jumbled, unsorted mess of all sizes.
No sorting like wind or water.
None at all. Glaciers just drop everything. This till often forms ridges called moraines, piled up at the edges or the end of the glacier.
Okay.
But you also get deposits from the meltwater streams flowing from glaciers. These are fluvioglacial deposits. And because water is involved, they're sorted usually sands and gravels.
Ah, so water sorts it out again.
Right. These form features like Esker's long, winding ridges of sand and gravel that were deposited by rivers flowing in tunnels under the ice, and Kames mounds or hills of sand and gravel dumped into holes or depressions in the melting ice.
Wow, glaciers leave behind some weird shapes. Eskers and cames.
They really do sculpt the landscape.
Okay, one more. Coasts.
Yep. Coastal or marine deposits. Waves and tides are constantly working the shoreline, moving sand and pebbles. The beach is a perfect example. Beach deposits sand, gravel, shells, sorted by wave energy. You also get spits and bars, which are ridges of sand or shingle built up by currents, often stretching across bays or out into the sea.
Like Cape Cod.
Parts of it, yeah. Good example. Then there are tidal flats, muddy or sandy areas exposed at low tide in sheltered estuaries. And sometimes, if land has risen or sea level fell, you find raised beaches, old shorelines, now stranded high above the current sea level.
So much movement. Wind, rivers, glaciers, waves.
It's constant change, and all these processes create distinct shapes on the land surface we call these landforms. Recognizing them is like reading the story of how that landscape formed.
Yeah, you mentioned some strange names earlier, like drumlins.
Ah, yes. A drumlin is a classic glacial landform. It's a smooth, elongated hill made of till, shaped like half an egg or an upside-down spoon. The steeper, blunt end point towards where the ice came from.
Tells you the direction of ice flow. Cool. What about an esker again?
The esker is that long, winding ridge of sand and gravel, like a snake across the landscape. It's the path of an old meltwater river under the glacier.
And the alluvial fan?
That fan-shaped pile of sediment where a stream comes out of the mountains, very distinctive from above.
Okay. Any others?
How about a roche moutonné? French name, means sheeprock. It's a bedrock bump, smoothed and streamlined by ice on the upstream side, but plucked and jagged on the downstream side. Shows ice direction again.
Smooth one way, rough the other.
Exactly. A spit, we mentioned that finger of sand sticking out from the coast. A river terrace, those step-like features in river valleys. And kettle holes.
Kettle holes.
Yeah, they're depressions left behind when huge blocks of ice, buried in glacial outwash, finally melted, causing the ground above to collapse. They often fill with water, becoming small lakes or ponds.
So these landforms are like crews left behind by these giant forces.
Precisely. The ground tells a story if you know how to read it.
So it's really clear the ground beneath our feet is anything but quiet or boring. It's this incredibly dynamic canvas constantly being shaped and reshaped.
Absolutely. From rocks breaking down over millennia to rivers carving valleys, glaciers reshaping continents. It's a record of Earth's power.
And understanding these deposits, the stuff on top, it matters for building things safely, for growing food, even just for appreciating the landscape when you're, out hiking or on vacation.
It connects us to the planet's history and its ongoing processes. It helps us understand where we live, quite literally from the ground up.
So next time you're outside, maybe take a closer look. That hill, that ditch, the soil in your garden, it all has a story. The ground isn't just static dirt, it's a living record. And maybe think about this. What new landform, maybe tiny, maybe huge, might be forming right now, somewhere on Earth, completely out of sight, just waiting to be discovered?